today we'll talk about marine valves indeed, and especially I want to take an example that I have studied these last years, which is a sediment sequence offshore the Nile River, and which is tracing paleofloods of the Nile during a period of very extreme monsoon. Excuse me. Let me take a bit of water. So marine valves, I guess many of you know this paper from Arnd Schimmelmann and co-authors, mostly from the Varves Working Group, which was a super nice review on marine valves around the world. And as you can see, there's actually quite some places which have reported some valve sediments. And some of them are, let's say most of them are related to oxygen minimum zones or stratification in the ocean. Another part which is a bit special is the eutrophication, which happens in the Baltic Sea. And then there's another bunch of other factors leading to the formation of valves in the ocean. But I can only encourage you to read this paper, which is really exhaustive and informative. So now we're gonna focus on the Mediterranean, where valves have been identified in different places, and I will focus only on two main examples because they are also very different. So the first example has been published in '99 by Kemp, and it's a valve sequence. So it's floating valve, so it's never been completely proven, but it looks like this is a seasonal deposition. And mostly composed of diatom mats, and most probably related to changes in stratification between the summer and the winter. So this is the core which is from the Eastern Mediterranean and pretty deep. Excuse me. And what I want to talk about today is other types of valves that we found offshore the Nile, and these are parts of deposition during sapropel events. And I will talk a little bit about sapropels, what they are and what they represent in the Mediterranean. So here I show you two examples of valved sediments. One is on the left-hand side, you have these very dark colored sediments. These are the typical sapropels we find in the Mediterranean, and they contain more than 2% of TOC. That's how they are defined. And on the right-hand side, you have this valve sequence, which is actually a sapropelite because it contains less than 2% of TOC. So valves are found all over the Mediterranean, and especially in the eastern part. That's where they are the most well developed. The reason, so in the site offshore the Nile, I will argue that the valve formation is mostly due to phenomena similar to what happens in the present-day Baltic Sea, with stratification of water masses, but especially eutrophication. And I will show you why I think this is the case. Just to come back on the valve story, so this is it's related to what happens on land. So we have to keep in mind that North Africa is fed by the summer monsoon, and that's what is triggering the main runoff in the Nile River. So what you see on this map is the extent of the summer monsoon in the blue colors, and all these very colorful, so rainbow colors, are the precipitation evaporation in the Nile Valley, with the blue colors being the places where we have very strong precipitations, and especially in the summer. So this fresh water can be seen if we make a map of sea surface salinity during the summer, and you see in the upper map, you see these colors, with red being the very salt surface waters in the Eastern Mediterranean, but there's this lens of green colors, which is less saline water, and that's typically the runoff from the Nile, which is making this lens. But what you want to note here is this very high salinity in the eastern Mediterranean. So basically, the surface water enters from the Atlantic and will be progressively warmed and evaporated, and therefore enriched in salt. And because it's so rich in salt, it becomes dense enough that it will sink. So the circulation in the Mediterranean is a haline-driven circulation mostly, more than thermohaline, and it is very important. So for the present day ventilation of the deep Mediterranean, that this very deep, this very heavy water forms in the eastern Mediterranean. And you can see it coming when we increase the runoff from the Nile. We form basically we decrease the salinity. We form so that's this little sketch from Rudiment, from the book of Rudiment. You have the present day situation on the left hand side with relatively weak Nile runoff. Actually, it's during a precession maximum, but it doesn't matter. It's very similar to what happens now. So the Mediterranean is well oxygenated because of this haline forced circulation. And when you have a precession minimum, so an insolation maximum, you have very strong monsoons and a lot of fresh water running from the Nile to the Mediterranean, formation of a low salinity lead or surface water, which is blocking basically the whole circulation. And you end up with a deep Mediterranean, which is completely anoxic. And this leads to the preservation of these organic rich sediments, which we know as sapropel. So here is another little sketch to illustrate that. As you can see, I have quite some skills in drawing. So once again, large precipitations, large runoff, blocking of the ventilation and development of anoxia. And the conundrum is always, do we have anoxia because of high primary productivity or because of the high runoff from the Nile, low salinity? And this question has not been firmly answered, and I personally think it's probably a combination of both. And that's also why I think that the conditions leading to the deposition of varves in the offshore Nile River are really very similar to this eutrophication scenario of the Baltic Sea. So if we now look even more in detail on the let's see the deep sea fan of the Nile River, which is very, very big, and I have here a collection of different cores which are either published or which I studied in these last years, and which all contain some laminations. So I will first talk about the deepest of this core, which has been published by Marie Revel mostly, but also Emmanuel Ducassou. And they found these laminated sediments with the presence of clastic mud layers, which they related to very large floods all over the delta, basically. And so this was the first identification of laminations in this region. And the core is pretty deep. It's 1,500 meters deep. So I have also now studied a series of 3 cores, which are located between 700 meters deep and 400 meters deep. They have been correlated using basically their sedimentologic features. And here I show you the titanium calcium ratio, but it could be also done using magnetic susceptibility or the identification of different features in the core. I also dated it with radiocarbon, but I'm not going to go too much into details here. I just want to show you that so the 2 deeper cores contain these laminations pretty well preserved, while the shallower one at 400 meters contains only some laminated parts and mostly very faint laminations. So I have, we published a paper last year talking about that. Basically, I propose that we are at 400 meters, we are really at the limit of the oxygen minimum zone of the development of this anoxic part in the Mediterranean. So that's really the upper level of this anoxic boundary. So here is a little overview of the Varves and of the, let's talk about laminations first. So here is in the deeper core, and you can see the laminations are extremely well preserved. That's the core we are going to talk about mostly. But there are also varves or laminations in the intermediate core, whereas it's very faint in the upper core. Also, yeah, I wanted to mention, so it's not very easy to see on this figure, but basically the lamination types are very similar in these cores. I can recognize certain patterns of depositional sequence in the three cores. So basically, I worked on this core for quite some years, but I was looking at mostly low resolution records of so geochemistry. And I thought at GFZ it would be fantastic to use the techniques that are developed for lakes to study this lamination sequence. And I must say, we didn't know what we were looking at. There was a hypothesis that these were flood layers, but we didn't know, and we didn't know the cyclicity of these deposits. So that's what we were looking for. So I used also some really nice tools that are at GFZ, like the Tornado, which is mapping elements in thin sections or sediment blocks. And this is super nice because it can be matched directly with thin sections, and that's a very interesting tool to identify layer boundaries or type, and count varves and count the layers. So I'm going to focus now on this part of this thin section, and basically what is interesting is that I could recognize a series of 4 sublayers that are repeating themselves. So that here I show you as colors, so black, pink, gray, and yellow, and this is a repeated sequence. Sometimes some of these layers are absent, but in most of the sequence, these 4 layers are present repeatedly. So if I go again, if I zoom again, and now you can see the bar at the bottom is 1 millimeter. So we are having a look now at this sequence of 4 sublayers. And I will start with actually the DL2, which is the black one. This is a coarser detrital rich layer. With we can really see individual grains, and it's mostly, there's barely any organic matter. It's mostly sediment, detrital sediments. Then there's a layer above it, which is a mix of foraminifera, very coarse material, and quartz grains, and some coccoliths and things like that. And then above it, that's the gray layer called DL1, and that's a very fine layer where grains can be recognized, but mostly it's a matrix which is really, really fine. And on top of that, and this one is not always present, that's this LL2 in yellow. And that was very intriguing. It's a layer containing a lot of very, very fine carbonates. It's so fine that I even had primes to make SEM, electron microscope images. But I did succeed, and so I had a look under the microscope, under the SEM, at different layers. So the detrital layers, they really contain these aluminosilicates, and then some titanium iron oxides, whereas these very fine carbonate layers, they contain some quartz and some silicates, but they are seemingly coated with calcium. And if we are lucky, we can see some calcite needles also growing on silicates. So yeah, so there's more, I mean, in the paper, there's more analysis on XRD, so the mineralogy, and I invite you to have a look if you're interested. So once again, to sum up, we have these 4 different layers, 2 layers of detrital grains, one is coarser than the other, and 2 layers of carbonates. One is very, very fine, the other one is coarser and contains some foraminifera which are very easily identified. So this is the hypothesis that I had for the depositional regime of these layers, so their interpretation. I suggested that the black layers, this very coarse detrital layer, was deposited during the summer and was really an expression of the summer floods. And there's a process by which you can transport sediment-loaded freshwater plumes downslope through diapicnol mixing. So once again, we can talk about that. I will not enter into details, but this is actually quite well studied. And these summer floods are pretty strong, and even in the Nile. So what I show you on the right hand side down below the sketch is a plot of the discharge of the Nile, Q, which is this black line, and the proportion of fine sand in the suspension load of the Nile River. And you can see that when you have high discharge, basically that's when you have these fine sands that are transported in the Nile River. So that's also why I thought that this coarser detrital layer was an expression of the Nile floods. Above it, oh, and yeah, I wanted to mention as well, because the Nile River is extremely big. It's 7,000 kilometers long, and there are 2 sources basically. But the one which is important for our study is the Blue Nile, and you can see on the picture, it's during the summer flood. It's very sediment loaded. The White Nile, which is the lowest picture, is also a pretty active river with a lot of topography, but it encounters downslope the Zout marshes, which are actually a sediment filter. So nowadays, most of the sedimentation in the Nile is influenced by the Blue Nile, and I have some figures about that. So once again, we can discuss that later. So after these flood layers, there's this layer of carbonates with some foraminifera and coccoliths in it, which I propose is a plankton bloom, and occurred in the autumn after the flood. And this is because I found this paper actually from 1967, where Halimetal mapped and documented plankton blooms offshore the Nile River after the last natural Nile flood. So basically before the huge Aswan Dam was built in Egypt, which is now trapping a lot of sediments and nutrients. But beforehand, there was basically a bloom every year, and it was so strong that you had local fisheries working only during the autumn. So it was a very seasonal, traditional fisheries that were operating in Egypt. So I think that's what we see basically when we have this bloom layer, so this foraminifera rich layer coming on top of the flood layer. Then we have the very fine detrital layer, which I suggest is deposited during the winter and spring, so when the Nile runoff is very low. And once again, it's this from the same study of Billy and Badri from the suspension load in the Nile River. And it's so we see the opposite picture, basically, with increases in clay during periods of low discharge of the Nile. And so that's why I think that's what we see also in our sedimentation. And finally, there's these very strange and mysterious, very fine carbonates, which are draping sometimes with very sharp boundaries, layer boundaries, but not always, and sometimes extremely dense. And I have been measuring their isotopic composition, which I will not present here, but once again, it's all in the paper. And I think that this stuff form when we reach very, very anoxic towards euxinic, so with free sulfides in the water. And these basically tend to form a lot of alkalinity, so a lot of carbonate ions. And as soon as you start having some delivery of calcium from the Nile River during the beginning of the flood, I think that this is creating this very depleted, basically isotopically depleted carbonates, and very, very fine. I suggest that they form in the water column, very close to the bottom, basically the water and sediment interface, and are forming just at the beginning of the flood. So that's my working hypothesis for the moment. So yes, if we sum all that up, I have a sort of an understanding of a seasonal cycle of deposition. And now the next question is, it looks like these are varves, but can we prove it? Because this sequence is a floating varve sequence. And so the top of the core is not varved, and I couldn't count or use any radiometric method to prove that. So what we did with colleagues here at GFZ, we used Bayesian statistics with the radiocarbon ages that I had to test our hypothesis of a varved sequence. And what I then did is count throughout the core. So I did that during the lockdown, took the microscope home and counted, measured all through the 5 meters long sequence of layers. And so that's what I'm going to show you now. So it looks like that. You have some very thick laminations, sometimes millimeter thick, and sometimes some very, very thin one. So basically, there's a very drastic change in the overall thickness of these layers, and this is mostly carried by the detrital layers. So both the flood and the winter deposition. So I counted more than 1,500 layers, and as I said, the thickness is mostly controlled by the flood layers, but also by the winter runoff. So that's what we did with colleagues at GFZ, mostly with Arne. We compared the counting I did throughout this core, using basically assuming that these 4 sublayers are 1 year, and using the thickness to calculate an accumulation rate. And we compared that with the radiocarbon ages, which were measured on foraminifera, so on planktonic foraminifera, which is nice because planktonic foraminifera have a very small reservoir age. They are basically almost forming in equilibrium with the atmosphere, so there are some corrections to do, but it's not like in organic matter in lakes where you can have really big reservoir ages. So these radiocarbon ages are already pretty good, but as you can see, basically some of them are reversed. And I was very puzzled about that when I measured these radiocarbon ages. So we used the Bayesian technique similar to what Bacon does, but except of using the prior from Bacon, we used the prior from the layer counting. And we tied the record at the top at 100 centimeters and let it run down, basically. And what's super nice is that it's matching very, very well. The layer counting goes through all the C14 ages within the error bars. And so it's a great way to test for the presence of Varve. And I think what's very nice is that it's improving a lot the accuracy, because if you have only C14 ages, you have to trust them. You have to trust that you will choose the right ones, the ones that are not reversed, but it's a bit arbitrary. Now with both the layer counting plus the radiocarbon, we have this really nice accuracy. We know that every point is within the error is actually pretty accurate. And there's also a very good precision. That's mostly at the bottom of the core. You can see that the error is in the order of 50 years, which is fantastic for ages that are older than 7,000 years. Okay, so, and also, yeah, I just wanted to point out, because there's a part of this core which is not laminated at the top, and that's where we have the largest error. So as soon as you have continuous laminations, then it becomes a very nice age model. So the first result is that we have this 15,000 year long annual Varves record of past floods of the Nile during the African humid period. And I will talk a little bit about the African humid period because it's super interesting, actually. It's a period of very strong humidity that occurred at the beginning of the Holocene in Africa. So when people say the Holocene is boring, this is not true. A lot of stuff happened in the Holocene. And basically during this period, there's many evidence from archaeology, from lakes, from marine sediments that North Africa was very humid. So this is a modeling experiment which shows the anomaly of precipitation, and you can see basically a positive anomaly of precipitation throughout North Africa in the core of the monsoon area, but also further north. For the Nile, this means that the Nile became a very big river, even bigger than today, with an extended fluvial network, a lot of smaller streams. And because the amount of precipitation was much higher at the source of the Nile River, there's also a threefold increase in the Nile runoff. Also interesting, Zaki et al. Have found recently some streams in Egypt which are covered with pebbles, with gravel. And they calculated the amount of rain and the intensity of the rain that you need to transport these pebbles, and found that there were some very heavy rainfall events in Egypt, and they could date it using luminescence, I think, back to the African humid period. So yeah, so we had a Nile River which was basically more a torrent than the peaceful river we know nowadays. Also important for understanding why we want to study the African humid period is that modeling studies suggest that this very strong monsoon is also favored by the fact that there were some really high surface temperatures in North Africa. So the more you increase the temperature, surface temperature, so air temperature, the more you will get your monsoon further north and stronger. So this is really interesting because we are looking at a time interval which can play the role of an analog to what we expect for North Africa. Also, again, modeling looked at the changes in Nile runoff if we start changing the hydrological cycle. And you can see all these colors and these traces that you see on both these graphs are individual runs from individual models. So the first thing you can see is, wow, there's quite a spread in the data. There is a tendency towards a stronger runoff of the Nile, and there is a tendency which is actually more significant towards a more unstable Nile River. So that's what these two images tell us. The only thing is that the spread is so big that we actually don't really know. And it's very important, therefore, that we have data, proxy data to test these models. And that's what we have with our Nile flood record. So here I show you only the Varves, so the continuous Varves records. So it's a bit less Varves numbers. And I just wanted to show you something that I calculated pretty quickly. So we detected some changes in the accumulation rate, which are these blue bars. And I use these change points to chop the core in 6 parts. And I compared for these 6 parts, basically the distribution of the layer thickness. And what you can see in this, so these are these violin plots that you can see at the bottom. What you can see is really striking is that when you have higher, so basically the mean is all these dots. I think it's the median actually. So the median thickness are the dots, and the spread is shown by the violin. And when we have these very thick layers, we also have the largest spread, which means we really alternate between a system which is producing a lot of erosion, a lot of sediment transported and deposited, and actually periods where we have very small layers, flood layers, and sometimes even no flood layer during the year. So, so this is actually pretty interesting, and if we think about what we saw in this model, that's basically telling us that probably indeed the Nile River has a good chance to become a lot more unstable as the hydrological cycle becomes more intense. So results number 2, we have large changes in layer thickness, and these thicker layers are associated to high amplitude variability, which means that when we have an enhanced rainfall, we have a lot of erosion in the system and a very unstable Nile River. So to sum up, I hope that I convinced you that we have a 15,000-year-long Varves records of past Nile floods during the African Humid period, recovered from the deep sea fan, and that we could identify some massive floods and a very unstable fluvial system during the African Humid period. In terms of outlook, we want to now use time series analysis to determine the main forcing factors of this record. And as I said, if you want to know more, there's a paper already in Climate of the Past, which you can check. So that's it. I thank you for your attention, and I'm happy to take any question.
Thank you very much, Cécile. Super interesting talk.